and welcome everyone. Nice to be here. So I'm going to be talking about 5 tips for better pandas code. And so as was mentioned, I do a lot of training around Python and data science. So if you're interested in that, I have a lot of books and content. You can reach out to me on Twitter or LinkedIn, or I've got my email here as well. I'm actually running a 6-week boot camp for people who want to get their hands dirty with some of the stuff I'm going to be showing today. So reach out if you're interested in that. Okay, so what we're going to talk about today is pandas. And let me just introduce the pandas library if you're not familiar with it. Pandas is a Python library for manipulating tabular or structured data that you would get from a database or data that you would get from SQL or CSV. And Python is a slow language. It's not particularly fast, but the dirty secret of pandas is that it's leveraged this library called NumPy, and NumPy basically, instead of being slow, makes it so it's fast. And due to the lack of time, I'm not really going to get into how that is, but basically by leveraging NumPy and pandas, you can basically write Python code that's basically as fast as C code. And so you get sort of the best of both worlds. You get really easy to write code, and it's fast and efficient. I'm going to be talking about some best practices for pandas. So Python is the most popular language for data science these days, and pandas is the most popular library for manipulating structured or tabular data. So I think it's a key tool to know and understand, and if you can wield it correctly, it's going to bring you a lot of benefits. So I'm going to talk about how to manage types in pandas, this thing called chaining, mutating information in pandas, function application, and then aggregation. So the data set I'm going to be looking at here, and this is a notebook. If you're interested in this notebook, you can reach out to me and happy to give you the notebook here. The data set that I'm going to be reaching out or using is vehicle data from the United States government. They basically post information about all the cars that are sold. So I believe this has from like 1984 to I think 2019 or something, all the makes and models with their associated fuel economy. So I'm loading the pandas library here as PD. I'm also loading a few other libraries here, but you can see that I'm using pandas 1.3.2, which is basically the latest version of pandas. However, 99% of what I'm going to talk about today applies to most versions of pandas that have been released in the past few years. So I'm just going to change the setting here to view a little bit more data. I'm going to load my data, read the CSV file, and then we should have this output right here. So this is a data frame in pandas. It's a 2-dimensional data structure similar to a database table or a spreadsheet. And this is the information from our data here. You can see that I have 41,000 rows and 83 columns. So a pretty good data set about what you see in a car, right? City mileage, highway mileage, make and model year, that sort of thing. Okay, so if you look at the columns here, you can see here's the 83 columns. So different types of columns, which is very similar to what you'd see in a database or a spreadsheet. So again, pandas makes this pretty easy to manipulate. So we're going to talk about the first tip for being effective with pandas is making sure the types are correct. So CSV files, comma separated value files, are super common. You see those all over the place. I've seen those in my consulting with companies. I've seen that in Kaggle competitions. I've seen that just in open data sets. A lot of companies will provide their data in CSV. Pandas can read CSV files. I mean, it can also read a bunch of other files as well, SQL or Excel or other formats. But a lot of times you do use CSV. And so CSV has the nice quality that it's human readable. And that's about the end of the nice qualities of CSV files. And so one of the drawbacks of CSV files is that they don't have type information in them. And so when you read a CSV file in pandas, pandas tries to infer the correct type, and it does an okay job, but not great. So if you use the correct types in pandas, it's going to make your experience in pandas a lot easier and better. And so I'm going to go through some of those issues that you might run into. I'm going to limit the types that we're looking at. So just a portion of those 83 columns, I'm going to select some that are numeric and some that are categorical in nature here. So if you pull out the types that I'm looking at from the CSV file that we just read here, you can see that we've got some int64 types, some floats types, some object types. So int64, if you're familiar with Python, is not a Python type. Again, that's because Pandas leverages this NumPy library under the covers. int64 is an 8-bit or an 8-byte integer. And so again, by using this library, you get that speed up. And we see float 64s, those are floating point numbers. And then we see objects. And so objects generally in pandas mean that they're string types or mixed types. And when you read a CSV file, if pandas can't infer a numeric type from it, it will tend to put it as an object type. So I like to go through my types and make sure that my types are correct. Another thing that might be interesting is just to look at the memory usage here. So I'm going to run this memory usage command and note that I do have the deep equals true option there. By default, when you run memory usage and you don't use that, it doesn't correctly report how much information the string columns are taking up. So this is the number of bytes for every column there. And if you sum that up just using pandas, you can see that I think this is about 19 megs. So we're using about 19 megs in this data set. So not a particularly big data set, but I want to just show you with some basic steps here that we can trim that down quite a bit. So one things that pandas has support for is integer types. We saw that int64. I'm just going to select all the integer columns here and do a describe on them. This is going to give me summary statistics for each of the integer columns. So you can see that like we have city 08, combined 08, highway 08. So that's mileage, miles per gallon for city combined city and highway. Highway, we've got fuel cost, how much someone would spend on fuel. And then the range, how far a car will go. That's an electric car. What's the range of an electric car? And then we have year. So these are all the columns that when we loaded our data set, pandas thought those were integer columns. Now there are some caveats with pandas and integer columns. If pandas comes across a column that looks integer-like, but it has missing values, pandas can't support that by default with this int64 type. So it actually coerces that column to a float 64. So floats, if you run into a float column, it could be all floating points, it could be floating points with missing values, or it could be integer-like and have missing values in it. Interesting in this code that I've run here is the summary statistics here. You've got the count, the mean, the standard deviation, the minimum, maximum, and the inner quartiles there. If you look at the maximum values for these integers, like city, combined, and highway, they max out like 150, 136, 124. So we're using an 8-byte integer to store those right now. And if you're familiar with computer architecture, you're probably aware that 8-byte integers can handle numbers a lot larger than 124. And so it might be the case that we're using a little bit too much memory for that. So just FYI, I would not write this code up here. I do code like this all the time. If you follow me on Twitter, you see that I don't post cat pictures, I post code pictures. And so I would write this in this chaining style here. So basically what I'm going to do is I'm going to put parentheses around it, and then I'm going to say, these are the steps I'm going to do. So let me just comment these out, and you can see what I'm going to do here. I'm going to take the data frame here, filter out these columns, and then I'm going to select these columns that are integers from those, and then I'm going to describe those. So I like to write it in this chain, one step at a time. It reads like a recipe, and you can easily see what you're doing there. Okay, so we're back to our integer columns. It turns out that, again, we're leveraging NumPy here. So if you use this NumPy command, info from that, you can inspect what the dimension or what the sizes are for an int 8. And it says it goes from -128 to 127. So it turns out we could probably use an int 8 for this highway mileage. If you look at the minimum value, it doesn't go below 9. So we could probably use an unsigned int and get away with that as well. We can do the same thing here with int 16. You can see int 16 goes up to 32,000. So all of these here, these integers that I have, could be represented with an int 8 or an unsigned int 8 or an int 16 here, and would save 75% or almost 90% of the space by just converting those types without any loss of fidelity there. So that's what I'm going to do here in this one. I'm just going to say, let's pull off these columns, and I'm going to convert these columns to int 8, a highway to int 8, city to int 16, combined to int 16. And then let's just look at what the description looks like after that. And you can see that even after that coercion there, we are not losing any fidelity there. So that's a lossless conversion, but we're going to save a bunch of memory by doing that. Here I'm going to select just all of the integer values after I've changed them, and you can see that that looks pretty good. So let's run our memory usage now after we've done that chain, and we went from 19 megabytes down to 18. So we saved about 10%, not huge savings, but again, 10% is better than nothing. Let's do the same thing with floats here. You can just select what we have as floats, and I have cylinders and displacement. If you look at cylinders, it looks surprisingly int-like. So I'm going to do a describe on that, and you see that like the minimum and maximum and the inner quartiles are all whole numbers, indicating that this is probably a column that had missing values in it. The engines did not have cylinders, and so because it had missing values, Pandas coursed that into a floating point instead of numeric. So let's just inspect that and make sure that's the case using this value counts from Pandas. You can see that indeed there is a missing value. 206 of them had missing values in there. So if we want to inspect where those values were missing, we can just, again, use Pandas here to do that. I'm going to say pull off these columns and then do this query. This is sort of like a database query where cylinders is missing. And you can see, like, for example, it's missing on this Nissan Altra EV, RAV4 EV, RAV4 EV, Ford Think. And if you look at these, there seems to be a somewhat common theme in that most of these, maybe with the exception of like the Subaru RX Turbo, tend to be electric cars, right? And I'm not a car guru by any means, but my understanding is that electric engines do not have cylinders, hence the missing value for cylinders there. So typically, if you have missing values, you should talk to a subject matter expert and figure out what the appropriate response is to deal with those. So what I'm going to do is I'm just going to make an executive decision here, and I'm going to say, okay, let's take our cylinders column, and I'm going to just fill in the missing values with 0. After I do that, I should be able to convert that to an int 8 and without any loss of fidelity. And then displacement, I'm going to fill in the missing values for displacement. That's engine displacement with 0 as well. And then after that, I'm going to course the types, and then we'll do a describe on that. So you can see I'm chaining these operations up starting from the raw data. And if I look at that, that looks like it's a pretty good operation here. You can contrast that with the original data. You can see that we're not losing much there. In fact, we're not losing anything there. You can do the same thing with NumPy, and you can inspect the floating point types. Floating point precision is a little bit different than integer precision due to the impedance mismatch between how decimal numbers are represented by the binary, i.e. EEE 754 standard. But it's possible that you might want to change your floating points from the default float 64 to some floating point representation with less precision, and that might be perfectly fine for whatever your uses are if you want to save some memory that way as well. So in my case, I'm going to convert the displacement here to a float 16 after I do that now. And so this might be an operation here to just sort of walk through these steps, these columns, and clean them up a little bit. Let's just look at my memory usage after doing all of these steps, and I'm now at 17.5. So not a huge savings, but a little bit of savings there. Let's proceed to objects. Remember, those are for strings. And I'm going to select the object columns. Here's all the object columns. So the first one looks like it's categorical, drive. Second one here looks a little bit weird. It's got parentheses in it. Third and fourth make and model look categorical. Tranny looks categorical, but it also looks like it has 2 values in it. It looks like it has automatic and manual, and it also has the number of speeds. So we probably want to split that into 2 columns. And then created actually doesn't look like a string column at all. It looks like a date column. So we need to tell Pandas to parse that as a date. So let's just inspect the first one here, drive. I'm going to do value counts on it, and it looks like pretty low cardinality. It's got like 8 entries in that, including some missing numbers. You can see some NaN in there. You might want to, again, query where those missing values are. Why do I care about missing values? If I'm going to do machine learning, a lot of machine learning algorithms don't like missing values, so I might want to dive into that. So you can see that the drive column is missing here, and it looks like for a lot of these, they are, some are electric, some are not electric, like a Corvette. So again, talk to a subject matter expert. You might want to check out why those values are missing and take the appropriate action from that. And so what I'm going to do is I'm just going to say fill in drive with any values that are missing, and then convert that to a categoric type. Now, what a categoric type does is basically, instead of storing a pointer to a Python string for every value in there, it's going to make a little mask. And since there's only like 8 unique values, it's going to make a mask that points to one of those 8 values. So you have a pretty big savings. This is where we start seeing a pretty big savings by doing this. We've dropped from like 17.5 megs to 12 megs by converting drive to a category and make to a category. So pretty big savings. If you're looking to save memory space, that's a nice, easy place to get some memory space here. Now, again, tranny, this looks like a column that has 2 values in it. So I might want to do something like this, where I say, let's just make a column called is it automatic, which is a Boolean column. And then we'll make another one called speeds, where we'll use regular expression to extract that, convert it as an integer 8. And let's look at how big my data is now. I'm now down to 10 megs. So I basically halved my memory, in addition to cleaning it up by doing these steps. But also note that I am working with the original raw data. I highly recommend that you work with the original raw data. Anyone who's dealt with reporting or machine learning, inevitably your boss comes and asks you a question. So it's good to have some provenance and go back, be able to tell where that data came from. We do want to change that date to a date. So I'm going to try and do that. There's a pandas to date time. I'm going to try and convert that to New York time. I get a warning here. It turns out that this created on has this EST column, which pandas really doesn't like. So I'm going to have to jump through a few hoops here. I'm just going to replace EDT by this offset and EST by this offset. And if I do that and convert it to a date, I actually don't get the warning that I had there before. And I'm just actually jumping on and saying, let's look at engine description now and try and parse out engine description. Engine description looks like a free-form text column, which is the bane of data scientists everywhere. Looks like there's these parentheticals, there's missing values like FFS in parentheses, FFS with spaces after it. So kind of a mess. Again, talk to a subject matter expert, see why that is. But what I'm going to do is I'm just going to take an executive decision, say, I think FFS, this fuel feedback system, is important. So I'm going to just store that and then drop the column otherwise. So we're going to pull off FFS from engine description and then drop it. And let's look at how much memory we're down to. Now we're down to 6 megabytes now. So almost a third of the data savings by doing that. And now at this point, this is a pretty good little chain of operations. I'm just going to push this into a function. And by putting this into a function, I can basically come back to my notebook, run this function, and I'm in a good place here using my raw data. So that is the first part of my talk. If you use the right types, you can have a potentially large amount of memory savings, which is important for pandas because pandas is a small data tool. And by small data, I mean it only works with data that you can fit into memory. Second part of my talk is about chaining, and I've basically shown you chaining as I built up that chain to do that. So I'm a big fan of chaining. If you read my book, best-selling book that just came out, Effective Pandas, talks about this. If you read the Python cookbook, second edition, I didn't write the first edition, but I wrote the second edition and basically rewrote all the code to use chaining that way. I'm a huge fan of that. If you write your pandas code in these chain styles, it's going to be a lot easier to read and understand. It looks like a recipe of steps. There is a method in pandas called pipe. So if you find a place where you can't really chain, consider using pipe to do that. So I would take this code here and put it into a little function like I've got here called tweak autos, load the raw data set, pass it through this function, and I'm good to go. This function reads like a recipe telling me each step along the way what I'm doing to the data. It's all in one place. I don't have to worry about it. I don't have to worry about artifacts along the way. Okay, contrast that with this data here. This is what 95+% of the data that you see on Medium and other places recommends you use pandas for. And they have data that looks like this. This is not even, this is only going up to make here. So And so it's not even all of the column. This is not even doing everything I did here. But if you look at this, there's a whole bunch of these settings with warning copy. And if you've dealt with pandas and you've copied people's bad code like this, you've seen these. You'll note that if you use my style here, you'll never see those issues. You'll never see those warnings or potential bugs and have to deal with that. And it's a lot easier to use. It's also easier to debug mine. You can see that I basically debugged it as I was building it up. But if I want to debug it later on, I certainly can. I can just leverage pipe. So I can use pipe to make a variable. I can just pipe like get var in there. And you can see I'm using pipe with get var, and I'm making a variable called df3. So when I run this, df3 will be the intermediate state after pulling out those columns. I can also comment this out, and you saw me do that before, where I commented out everything in the pipe and then uncommented as I was going. That's a great way to sort of understand what your pipe is doing. And I can also pipe to display. I can make a little function that will print out to display here. And here's one using a lambda right here. It's just going to display this code. So let me run this. You'll see that when I run this, it should print out an intermediate step here. So this, what it's printing out right here, this is the piped version. If you scroll down a little bit, you'll see that here is the actual output down here. So there is the output. And you can also see that I did call this create an intermediate variable here, this little pipe get var here. So if you wanted to have that intermediate variable here, it's now in a variable called df3. So you don't actually lose anything by using chains. You just make your life easier, you make your colleagues' life easier, you use less memory. But most people don't know about this, or for some reason don't write code this way. So I'm a huge fan of that. The next part of my talk is don't mutate your code. So a lot of people who see my chains are like, Matt, that's horrible. You're wasting memory. You're doing this the wrong way. There's an in place option on a lot of methods in pandas. And if you use in place, it will change things in place. Turns out there is an in place option for a lot of things, but it actually doesn't do in place most of the time. What it does is it makes a copy into the covers and then shims that back in. So you're not saving any memory by using in place, but what you're doing is, because when you use in place, it doesn't return anything, you're eliminating the opportunity to use chains. You're also mutating your data. If you're a software engineer, you know that mutation is generally something that makes our brains hurt. It makes it hard to debug our code and harder to reason about what's going on. In fact, there is even an issue in the pandas itself. I've linked to it here, the issue, but a comment from Mr. Reback, a core developer at Pandas, saying you're missing the point. In place rarely does actually something in place. You're thinking that you're saving memory, but you're not. And so the point of this bug or issue in pandas is actually remove in place from pandas, because they believe it's detrimental. I believe it's detrimental as well. In fact, I don't even mention in place in my book because I don't think you should use it. And if you don't use it, if you follow the chaining examples like I do in my book, you just pass over a bunch of potential bugs that you might have anywhere. Okay. I think we're doing okay on time, so I'm going to keep cruising along here. The next part is don't use apply. Again, if you look on the internet, I tend to read a lot of pandas material because I'm interested in pandas. I teach pandas to large teams, and I've taught pandas to thousands, and I write about pandas and I consult on it. So you'll see a lot of people who say use this apply method and it will make things easier. And so I'm just going to make this autos 2, which is my cleaned up autos data set from running my little function here. And let's, this is somewhat US centric. So let's do liters per 100 kilometers, which I believe is more rest of the world centric. And so if I wanted to convert miles per gallon for the city to liters per 100 kilometers, I could do that with this little function here. And I just pass in the function to that, and that looks like it works, right? I have a new series or column with that value in it. Note that I can also just do this directly. I can say 235 divided by that value. And if you look at these, they look basically the same. However, if you were to do a little benchmark on these, you'll see that this second option here is a lot faster than the first one. In fact, it looks like it's about 40 times faster by my little benchmark right here. So various times I've run it, it's been, anywhere from 30 to 60 times faster by doing that. Why is that? It's because, again, Python is a slow language. When you're using this apply up here like this, it's actually pulling out each individual cell value, converting it from that integer value into a Python integer, throwing that into the Python function. and doing that for each of the cells. When you're doing this, you're doing what's called a vectorized or broadcast operation that's happening using modern CPU architectures like SIMD instructions. And so you have a block of integers or floating point numbers, and you say, take 235 and divide it by that block. It does that on the whole block all at once, very fast. It doesn't have to go through Python to do that. And so you get that huge speed up and memory benefit from doing that. So actually recommend not using apply generally, and against many Medium articles, bad advice there. Now, there are some exceptions to this rule. So if you are dealing with strings here, for example, the make column is a string column. And if I wanted to, say, is this an American car? I might have to do some logic like this. And, is the value from that column in one of these here? And you can use apply to do that. You can also, turns out there's an is-in method on the column that does the same thing. And if you look at these, there's not really a speed up by using this is-in option. Now, this is because pandas do not have an optimized string representation for this. Note that if we converted it to a category, we'd probably save a little bit of memory, but because we've left it as a string, if you use apply with strings, strings are slow anyway in pandas. So if I'm fine with apply there, but for numbers, generally not okay. So just a few more time it here. I'm just going to time those, and we'll do some more timing here for like country. You can see that, in this case, we'll make a new column called country. And here I'm going to use a where instead of that. So this would be how I would write this if I wasn't using an apply here. And we'll see that in some cases, the apply, you can see that the apply is actually faster than doing this without an apply. So if you are using string manipulation with apply, I'm sort of okay with that. Just know that string manipulation is particularly slow it's Python speed. It's not Panda speed unless you're dealing with categoricals there. So just be aware of that. Okay, the next, so that's my previous step was be careful with apply. Again, if you are using numeric application, you probably don't want to do that because it's going to be going down a slow Python path. You want to stay in that fast C path if you can. My last tip here is to master aggregation. So Pandas is a tool for manipulating structured data. If you've done anything with SQL or Excel, eventually you'd run into like grouping and pivot tables, and Pandas can do those as well. So let's show how to do that. I'm going to say, let's group by the year and take the mean for each year. And if we do that, we can see that in the index here, we have the year in the index, and then all the numeric columns, we have the mean values for that. So, with 3 lines of code, it's pretty easy to do something pretty powerful like that. If you want to do like the max instead of the mean, you just change those if you want to. Now we can do even more. We can say, I want to pull off the the combined 8 column and the speeds column and just do the mean of that. And you can do that. Note that you can also pull off those columns after doing that. So I'm just going to time these, just a hint. If you are aggregating, but then you only want certain aggregations, you might want to pull off the columns before doing those aggregations. You can see in this case, if I pull off those columns first, it takes 12 milliseconds to run. If I pull them off after, it takes 33 milliseconds because I'm aggregating everything. So if you can make the computer do less work, you can save some time there if that's important to you. Okay, so I'm just going to load some styling here because we're going to do some plots here. So it's pretty easy to plot once you know these aggregations here. So I'm just going to tack on a plot to the end of this. And you can see that now I am plotting here. Speeds is green and combined as yellow here. Again, I just stuck on a plot there. So if you understand how to plot with pandas, if you just do a plot, it's going to do a line plot. It's going to plot every column against the index. This thing in bold here is the index. So combined is going to be a column as a line, and speed is going to be a line as well. So that really easy to add plots. Just stick on a plot there at the end and visualize that. And so once I've got something like this, I can say, let's look at the variance for each year. Okay, here's the variance. If I want to plot that, I can just stick on a plot and look at where the variance changed for each year. If I want to look at the standard deviation, I can pull out the standard deviation. If I want to look at the 30th percent quartile, I do quantile 0.3. That's the 30th percent quartile. Or I guess it's not the quartile, I guess it's the quantile because it's not a quarter. And you can plot that if you want to. If you want to look at the median values, you can just comment that out, stick on median right there, and there's the median values. So once you understand this chaining and the aggregation and plotting, it makes it really easy just to go through these very quickly and try them out and see what's going on there. You can even aggregate with your own functions if you want to. Now, I'm going to say I want to group by year and country, and I am making a new column called country here. And so here, if you look at this output here, you can see that there is what we call a multi-index. You have year and country here. So this is hierarchical index, which is pretty powerful. You can also make hierarchical columns as well. So for every year, we have all of the other countries and the US countries, and we can compare them to one another. Pretty powerful. I mean, I could write this as one line of code. I'm splitting it out into a chain and writing it as a few lines of code, but hopefully you can see that that's pretty powerful, and that if you master this, it makes it really easy to do some cool things here. Now, what I'm going to do in this one is, instead of just doing, in the previous one, if you look at this, I did just the mean. I did a single aggregation. This one, I'm going to do 3 aggregation. I'm going to do the minimum value, the mean value, and the second to last value. Second to last value is a function that I wrote that we call a reduction or aggregation function. It takes a series or a column and collapses it to a scalar or single value. So you can write your own if you want to. Pandas has a bunch built in. You can see that now I have a multi-index. I've got year and column or country here. And then I've got, for every numeric column, I've got the minimum value, the mean value, and the second to last value. So super powerful. Again, basically one line of code to do that, but I'm writing that as multiple lines of code here. In this one, what I'm going to do here is I'm going to do the mean for each year and country. And again, you can stick on a plot there. It will plot each line, and you can see there's each line. This is a little bit hard to see here if you look at the x-axis here, because it's plotting the index as the x-axis, and we have a hierarchical index. That's probably not what you want. You probably don't want a tuple of 1984 and other in there. So what I'm going to do here is I'm going to take that result that I had right there. I'm going to do this unstack operation. So this is a powerful operation. What it does is it pulls out the inner index and pushes it up into a column. So now I just have a non-hierarchical index here, but country, and it has moved up here as a column. So that's pretty powerful to manipulate the code that way. And then after that, I'm going to pull off the city 08. So let me just walk through this chain of what I'm going to do. So here's the unstack with city 08. And then I'm going to plot that. And so this is for each US and other, this is the mean of the mileage. And so you can see how those change over time. I can use this to stick the legend on the other side. If I don't want to do mean, I want to do standard deviation, I can just change that aggregation there, and there's the standard deviation. So very powerful. Once you master that, it can be a little bit of work, but pretty cool. In this example, what I'm going to do is I'm going to just add a rolling mean to that. So this is something that you see a lot with COVID. So here is our plot here that we saw up above, and you can see it's a little bit jagged. So if I want to smooth that out, I can do a 3-month rolling average by just put rolling 3 and then do a mean on that. And you can see that that smooths that out. So really easy to do that there. Okay. That is my last tip, mastering aggregation. So in summary, Pandas is super useful, super powerful. Like I said, I've taught this to the biggest companies in the world, and they use it for really fast insight. If you use the correct types, you're going to save a lot of memory and make your code faster. If you write your code in chains, as I said, I recommend in my book, Effective Pandas. And as I've shown here today, it's going to make it really easy for you to understand your code. It's going to make it easy for you to collaborate with others. It's going to make it easy for you to test your code. It's going to make it easy for you to come back to your notebook easier. Highly recommend that you adopt that if you're not. Don't mutate your code. As I said, there aren't any benefits to doing that. Again, apply is a slow path generally in pandas. If you're doing that, you're going in the Python land. You want to stay in that fast C land if you can. And also aggregations are very powerful. If you want to leverage them, try them out. Once you start mastering them, it's going to open the doors. I do have a link here. If you use this code book 20, that will give you 20% off effective pandas in my store. Anyway, don't know if we have how much